What if I told you the biggest breakthrough in AI came from solving a children's game? Think about the telephone game. RNNs process sequences exactly like that. Each step only sees the message from the step before. And just like telephone, the message degrades, fast. By step 50, the original meaning is almost completely gone. But what if we could let every word see every other word directly? In 2017, researchers asked a radical question. What if every word could talk to every other word directly? No more telephone game, no more information bottlenecks. Instead of sequential processing, imagine a conference call where everyone can hear everyone else. That's attention. Watch this transformation. A sequential chain explodes into a fully connected network. Every single position can now attend to every other position in parallel. The first word can see the last word, the middle can reference the beginning. But here's where it gets brilliant. The model doesn't just see everything, it learns what to pay attention to. It's not random connections. It's learnable, intelligent information routing. Think about reading this sentence. The cat that chased the mouse sat on the mat. When processing sat, the model needs to know that cat is the subject, not mouse. Attention learns these relationships automatically. But how does this magic actually work under the hood? Let me show you the three components that make it all possible. Every attention mechanism has three essential components: query, key, and value. Think of it like a library retrieval system. The query is your question. What am I looking for? The key is what each book offers. This is what I contain. The value is the actual content. Here's what I can contribute. Now watch how these work together. Every position in your sequence gets transformed 3 times. The same input becomes 3 different representations through learned weight matrices. Q equals input times W underscore Q. That's your query matrix. K equals input times W underscore K, your key matrix. V equals input times W underscore V, your value matrix. But here's the critical insight. Queries and keys work together to determine who talks to whom. When a query and a key are similar, they have high compatibility. That compatibility score determines the attention weight. High weight means pay a lot of attention here. Low weight, mostly ignore this. Then, values determine what information actually flows. Let's see this in action with a real sentence. The cat sat on the mat. When processing the word sat, it creates a query. I need my subject. The word cat has a key that says, I'm a subject noun. Their compatibility? High. So sat pays strong attention to cat. Meanwhile, mat has a key saying, I'm a location noun. The compatibility with sat looking for a subject? Much lower. This is learned matchmaking for information. The model learns what patterns to look for, what connections matter. And it does this for every single word, with every other word, all at once. Now, let me show you the elegant mathematics that makes this possible. The beauty of attention is that it's just 4 mathematical operations. Let me walk you through each step with real numbers. Step 1. Compute compatibility scores. We take our query matrix and multiply it with the transpose of our key matrix, Q times K transpose. This gives us a score for every pair of positions. Watch. A 4-word sentence creates a 4x4 attention matrix. Each cell shows how much word I wants to attend to word J. But wait, step 2 is crucial, scaling. We divide these scores by the square root of the dimension size. Why? Without scaling, the values explode during training. Large values push softmax into saturation regions where gradients vanish. The scaling keeps our gradients healthy and training stable. Step 3. Apply softmax to create a probability distribution. This transforms our raw scores into weights that sum to 1. Now, each position has a probability distribution over what to attend to. High scores become high probabilities. Low scores, nearly 0 attention. Finally, step 4. Use these weights to aggregate the values. We multiply our attention weights with the value matrix and sum. Here's what makes this mechanism so elegant. First, it's completely differentiable. Every operation has smooth gradients. The model can learn through standard backpropagation. Second, it's parallelizable. Unlike RNNs that process sequentially, attention computes all positions simultaneously. That's a massive speedup. Third, the computational complexity. Yes, it's O of n squared. Every position attends to every other position. But here's the key. It's quadratic in sequence length, not time steps. RNNs, they're linear in sequence length, but can't parallelize. For modern hardware optimized for parallel computation, attention wins. Let me show you something fascinating with our attention patterns. Watch what happens when we adjust the scaling factor. Without scaling, the attention becomes extremely peaked, almost one hot. With proper scaling, we get smooth, learnable attention distributions. This simple formula revolutionized AI. But one perspective isn't enough. Let me show you why we use multiple attention heads. Here's a question. Why limit ourselves to one attention pattern? Different relationships require different types of attention. That's where multi-head attention comes in. Instead of one set of QKV matrices, we create 8, or 16. Each head learns to look for different patterns. Watch this visualization of BERT's actual attention heads. Head 1 specializes in syntactic dependencies, connecting subjects to their verbs. Head 2 learns semantic similarity, grouping related concepts together. Head 3 focuses on positional patterns, attending to nearby words. Head 4 might specialize in co-reference, linking pronouns to their antecedents. This specialization emerges naturally during training. No one programs it. The model discovers what patterns are useful for the task. Here's the computational trick. All heads process in parallel. We split our embedding dimension across heads, not duplicate it. With dimension 512 and 8 heads, each head works with 64 dimensions. After all heads compute their attention, we concatenate the results. Then, one final linear transformation mixes information across heads. Think of it as an ensemble of experts, each with a different specialty. Together, they capture the full complexity of language relationships. But there's one critical piece missing from our attention mechanism. Without it, attention has a fatal flaw. It has no idea about word order. Here's something surprising. Attention is completely position blind. The sentence, "The cat sat on the mat," produces the exact same attention as "Matt the on sat cat the." Completely scrambled, same result. Attention treats input like a bag of words, not a sequence. The solution? We inject position information directly into the embeddings. Every position gets a unique signature, a positional encoding. The original transformer uses sinusoidal patterns, sine and cosine waves. Different frequencies for different dimensions create unique position fingerprints. The beauty? These patterns extrapolate to sequences longer than training. Modern models often learn position embeddings instead. More flexible, but limited to positions seen during training. With positions restored, attention knows both what and where. Now you understand the engine powering modern AI. Let's see how this mechanism conquered the AI landscape. 2017. The Transformer paper introduces "Attention is all you need." Machine translation quality jumps overnight. Google Translate is transformed. 2018. BERT arrives. Bidirectional attention understands context from both directions. 2020. GPT-3 shows that scale plus attention equals emergent abilities. 175 billion parameters, all connected through attention mechanisms. 2022. ChatGPT brings attention-based models to hundreds of millions. But it's not just language. Vision transformers process images with attention. DALL-E generates images. AlphaFold predicts protein structures. The same attention mechanism, infinite applications. Let's recap this revolutionary mechanism. We went from telephone game to conference call. Query, key, value. The Trinity that routes information intelligently. Multiple heads for multiple perspectives. Simple matrix math creating intelligent behavior. This is the foundation of GPT, BERT, and every modern language model. You now understand the key to modern AI. One mechanism, infinite possibilities.